Hey, it's happening. We're going to keep plugging through. This is exciting stuff. I promise that I will not make how to design a survey for demographics the most boring thing you've ever heard. Starting with the color scheme. Guys, look, it's bright. We're here. We're excited. All right, what makes a survey useful for demographics? This is my cranky old lady talk where I'm like, don't do any of this. Okay. So for an overview of the talk, I'm going to explain why on Friday morning after 5 days of talks, you should care about this talk. What makes the survey good for demographics, things to do, in capital letters, things not to do, which is where I particularly get on my soapbox and rant. I will not leave you in the lurch. I will provide you examples of how to do this. And finally, at the end, all of this information that I'm presenting has been drawn from many resources that I will point you at. Because it's a lot to fit into 25 minutes. Okay, why should you listen to this talk? Okay, do you want to perform a survey to do exoplanet demographics? Do you want to decide if a pre-existing survey is useful for you to do exoplanet demographics with? Do you want to know how not to use data from such a survey to do exoplanet demographics? And will you ever referee papers on any of the above? The point is everybody in this room should have at least a high level understanding of some of these concepts. So it's important, everyone stick with me. What is the problem we're trying to solve here? Okay. You've heard a whole bunch of talks this week about all of the amazing discoveries we found. This is a quote from Astro 2020. To understand the formation and evolution of planetary systems as products of the process of star formation and characterize and explain the diversity of planetary system architectures, planetary compositions, and planetary environments produced by these processes. That's the goal, understanding. Here's the problem. Current knowledge of the demographics and characteristics of planets and their systems is substantially incomplete. Well, I took that personally. The problem is not that we actually don't have enough data. Now, that might surprise you because a lot of people are going to come down and be like, we need more data. The problem is not that we need more data. We have scads of data. This is the Exoplanet Archive. I'm the lead scientist of the Exoplanet Archive, so I'll take a little moment to say, reach out to me if you have questions or comments or compliments for the Exoplanet Archive. I accept all. But I wanted to point out a couple of things. One is that we have 130 million light curves at the Exoplanet Archive. Just in case you didn't realize, tons of data. And we also have nearly 6,000 planets. And in fact, in just a couple months, we will probably cross that mark of 6,000 planets. Now, can anybody guess how many exoplanets we had before we tried to do demographics? Any guesses? Someone throw a number out. The first paper I can find has 4. After they had 4 giant planets around solar type stars, they were like, wow, they're all around metal rich stars. That's kind of cool. So we have nearly 6,000 planets now. Why are we still incomplete in our understanding of demographics? So here is a plot showing those nearly 6,000 planets as a function of semi-major axis, their orbital distance from the star, and their mass in Earth masses, all normalized to 1. So at 1 and 1 is the Earth. So these are the solar system planets. And then these are all the planets found by transits, radio velocity, microlensing, and direct imaging, all of which you've heard about this week, or we'll hear about some more later this afternoon. So there's lots and lots and lots of planets. So what's the problem? Now, we're going to do this family feud style. Why don't we have fantastic demographics yet? I'm going to say that half of the room is family A and this half of the room is family B. There are a bunch of answers hidden on this screen. Why don't we have fantastic, complete demographics yet? Someone throw an idea out. Not enough what? No, this side of the room. Someone, any ideas on this side of the room? No. This side of the room. Observational incompleteness is on the board. This side of the room. Family B, come on back. What's something we need that we don't have? Sensitivity, I'm going to say that's like observational completeness, but I like the direction you're going in. This is the right sort of thing. All right, let's find out what the answers are. All right, between all of these different surveys, there are missing data. There are no selection criteria with which you could compare two samples. There's no detection criteria given for some of them, or noise models, so you would understand how significant this detection is. There are model and methodology differences between the different surveys for how they detect a thing and how they model a thing. There are sample size differences that aren't explained in ways that are useful. Some of the surveys have no false positive or false negative rates, so you don't know what they should have found versus what they didn't find. And there are often calibration offsets, systematic calibration offsets in how one survey does something versus how another survey does something. So there are a bunch of reasons why you can't just look at that plot of 6,000 planets and do demographics yet. And the one big thing that couples all of these together is that people don't publish enough metadata on their surveys. They don't provide enough information for other people to be able to use their detections to do cool demographics. Now, Daniel was saying, for instance, that if you find a hot Jupiter these days, you're not going to win a Nobel Prize anymore. That doesn't mean that hot Jupiter is not useful. If you provide enough information about it, we can use it for demographics, right? That's super exciting. So my goal with this talk is to make sure you guys understand the sort of information you're either providing if you're doing a survey or looking for if you're assessing whether a survey can be used for demographics. Okay, so do's. What do we need you to do if you're creating or evaluating a survey for demographics? And I will say a lot of this is drawn from the SIG2 report, the Science Interest Group 2 report, which I'll put up a QR code for at the end of the talk, which was a group of experts from all of the major detection techniques got together and said, this is what we need in order to combine transits with radial velocity with microlensing with direct imaging, any of the above with astrometry. This is what we need you to tell us. Okay, so does the survey have either the survey you're designing or the survey you're assessing? In terms of its survey properties, does it have stated detection criteria? Is there a threshold above which something is a detection and something is not a detection? Is it consistent across the survey? Is it someone looking at their image and being like, that looks good? That's not great. Is it a signal to noise threshold? Are there other things like a minimum number of transits that's involved? What are the detection criteria for something to be detected in your data? What models are being fit to the data? Are you fitting a transit model? Are you fitting a box least squares? This is a transit example, but analogously for direct imaging, for instance. What models are you fitting? We need to know. What's the observing baseline? And importantly, especially for things that aren't like transits where you're kind of doing a survey of one big field at once, but radial velocity where you're going target by target. What's the observing baseline for each target? How many points did you get? How do you handle multiple star systems? That's really important, right? And it's okay if you don't do it well. You just have to tell us what you did so we can quantify how it changes our answer, okay? I'm not saying solve the problem of binary stars in your sample because then everybody will just run away and be like, it's too hard. That's okay. There's going to be binary stars in your sample. Just tell us how you dealt with them, preferably in some quantifiable, repeatable way. And finally, in big capital letters, because this one's a big one, a detection efficiency, right? How many times would something have been in your survey and you should have detected it, but you missed it? For various reasons. But it's important to know, because then we can use the data that you put out and correct it for this detection efficiency. But if we want to use a survey for demographics, we need to know this. What's the detection efficiency? So here's an example from Kepler. As a function of the signal to noise, what fraction of the signals were detected. The red curve was the hypothetical detection curve for a threshold of 7.1 sigma, and the blue was an injection and recovery experiment that I did. And you can see that, there's some daylight. There's some daylight between the hypothetical performance and the real performance. I'm also going to take an aside here to say this number, 7.1 sigma for Kepler, was very specifically chosen for Kepler for 100,000 targets and 22 million observations per target. This is the number, this is the detection threshold you need for no statistical false positives. 7.1 is not some magical number that you can apply to any other data set. No other transit survey should use 7.1. is what I'm saying. I'm looking at everyone. Don't use 7.1 if you're not Kepler. Okay. All right, so that's how the survey is set up. Your stellar sample, all right, what stars are you looking at? Do you have a large enough sample of stars to do the interesting science that you care about? And I'm going to come back to an equation for this later. And do you have selection criteria for those stars that someone else can therefore use to understand how your sample fits in with a bigger sample? This was, for instance, a big problem with trying to compare Kepler and K2, where Kepler was one big target list that had been chosen from one big catalog, and K2 was dozens of different people's favorite target lists jammed together into one big target list, right? That made it more difficult to kind of reverse engineer what population of stars did K2 look at well. What stellar parameters did you use, and how did you derive them? And please, please, for the love of God, how did you uniformly derive them? Okay, I don't want to see a survey where you got these stellar parameters from this technique and this stellar parameter from this technique. There's going to be offsets. It's going to be hard to calibrate. Do it uniformly. Tell us how you did it. Which stars did you throw out? You have a selection criteria. That's great. You probably threw out some stars, which is fine. Again, I'm not saying don't throw out stars. I'm saying tell us how and why. So we, again, can reverse engineer how to use it. How noisy are your stars? Here's a plot over here for Kepler showing as a function of Kepler magnitude, the parts per million CDPP, which is basically a measurement of noise, showing that, you know, the dashed line here is the photon noise floor, showing how close we got, but not all the way there. And this is over here, this is a Kepler and K2 stellar example showing again that, you know, it's much more difficult to do this when you don't have one big, large, uniform provenance for your stellar parameters. And then finally, if you're only using one set of data, do you have a big enough sample size for your science? That's important. Okay, planets. I just realized nobody started my timer, so I don't have a way of knowing how much time has gone. Okay, great. The planet catalog. Okay, so you're trying to use a survey for demographics or design a survey for demographics. Hopefully, you're looking for planets. Maybe you even found some. Congratulations. All right. How did you measure the planet parameters and how did you fit them? Did you fit a model? What kind of model? From that, did you derive parameters uniformly? I hope, please, uniformly. I've capitalized all the most important words here to make it as easy as possible. Uniformly derived planet parameters. And which models did you use for that? For this planet catalog that you've made, what's the reliability? This is the false positive rate. How many times did you call something a planet, but it's not a planet? And did you account for both astrophysical and instrumental sources of false positives? I'm making it sound really hard. We just need to have an idea. You can have rubbish reliability, and in fact, Kepler does. It does. This is the reliability of Kepler as a function of period, as a function of the signal to noise. So low signal to noise, long period things have a rubbish reliability. That's fine, as long as we know what the reliability is and we can correct it. Okay, that's what I'm saying. I'm not saying the catalog has to be perfect. I'm saying we have to know how not perfect it is. That's all. Okay. This one is very technical, but I'm putting it here because I want these ideas in your heads as you think about data in this era of open source science practice that we're moving into, and all of the early career people here in the audience will be working within. Open science data principles include this idea of fair data. So findable, accessible, interoperable, and reusable. If you are creating a survey or assessing a survey, these are 4 data principles that you should be thinking about. I'm not going to read all of them individually. There's a QR code at the end for more detail. And again, this is more for people like me who have to archive large data sets and disparate data sets that all come from different places. But the thing we're aiming towards, and you thinking about data in your workflows, should have these ideas in your head: findable, accessible, interoperable, reusable. Okay, those are the do's. Now you know how to make a survey. What not to do? This is my rant. Okay. No manual vetting. No manual vetting. No manual vetting. Don't do it. When you're starting out with your project, if you need to do some manual vetting at the start to get a handle on what's happening, fine. But don't have a final catalog that includes manual vetting if you want your survey to be used for demographics. We need to be able to quantify how complete and reliable it is. And if you do manual vetting, we can't do that, right? You people sitting here after your caffeine just now would call a different thing a planet than you did 45 minutes ago at the end of that session, sitting there waiting for caffeine. I'm telling you right now, because it was me for many years. No manual vetting. Okay. More detailed things, don't host your data on your institution's server. Your data's utility will outlive your institution's server. I promise you. I promise you. Unless you're at some big government federal data center, your data's utility will outlive your institution server. Don't invent a new data format or data standard. I promise you one already exists that does what you need it to do, that other people know about, that there's Python code to already deal with. Don't invent a new data format. You don't need to, I promise. Don't assume you know all the use cases for your data, right? You had an idea when you created your survey, but other people might come later. You know, Hubble was designed and flown before we knew of planets around sun like stars, and you just got to see a whole bunch of spectra from Hubble on exoplanets. Don't assume you know all the use cases for your data. So provide enough machine-readable metadata so that other people can use your data for what they need. Don't throw away data without explaining and quantifying why, right? This is, again, you don't know what other people might want to use it for. So if you're going to throw away data, have a really good reason why and a really well-stated reason why. Don't publish your detections and sit on your non-detections. This makes it really hard to use your survey for demographics, right? Your non-detections are just as useful for demographics as your detections. Interestingly, there was a Nature article that came out this week, which was like, why don't scientists publish null results? And I was like, dear Nature, you tell me why scientists don't publish null results. Show me the last null result published in Nature. So don't publish your detections and sit on your non-detections, okay? That's not good science. And then this space reserved for your pet peeve. This is my collection of working with archival data for 15 years. And there are more problems, but this is the high-level things that I don't want you to do if you want your data to be used for demographics. And I promise you, I want your data to be used for demographics. All right, I promised you I wouldn't leave you in the lurch, so let's do two very quick examples. Which planet catalog should I use for demographics? Kepler or the NASA Exoplanet Archive? Now thinking about everything we said with the do's and the don'ts, what you need to know about your planet parameters and your stellar parameters and how they're derived, but we want them to be uniform. Put your hands up if you would rather use Kepler to do demographics. Okay, put your hands up if you'd rather use the NASA Exoplanet Archive to do demographics. I am here to say, never use the Exoplanet Archive to do demographics. It fulfills none of these criteria. The NASA Exoplanet Archive is a superset of many surveys that contains none of the required metadata that you need to do demographics. So if you take nothing away from my talk, and maybe you don't, please don't use the NASA Exoplanet Archive for demographics. Thank you. Okay, let's actually do a real thing. And this is my chance to plug SHIRA, which otherwise I wouldn't get a chance to talk about, but I would really like to. SHIRA is a SMEX mission concept to search for small planets in the habitable zones of binary star systems with relative astrometry that I'm the PI of, and it's very cool. But let's ask how we would design a survey that answers this question. How many widely separated binary stars do we need to survey for small habitable zone planets to determine whether the occurrence rate of those planets is similar to single stars? Okay? So if you're asking NASA for a ton of money, you better have a hypothesis that you're testing and testing well. So the hypothesis here is that small planets around widely separated binaries occur at the same rate as in single stars. This has really important implications for things like how do planets form, the physics of planet formation, but also thinking about future missions like Habitable Worlds Observatory, how much do we weight or de-weight binary stars in those searches for Earth-like planets? Now we know for binary stars that close-in planets are suppressed. There's a lower rate of close-in planets around binary stars than around single stars. But we don't know if that holds at habitable zone separations. We just don't know. But we can ask the question, how many stars would we need to look at to answer this, right? And so this is to help you guys think about this question of how big does my sample size need to be do my science. This is the only equation in my talk, I promise. You're okay, stick with me. It's a Poisson probability. The probability of k events in interval t. So here R is the occurrence rate. In this case, we're going to use the single star occurrence rate because that's the hypothesis that we're testing. T is the number of targets, the number of binary stars that we're going to look at in our sample. And K is the number of planets that our putative survey detects, right? So we want to set up this question so that we look at enough targets that we can say something statistically interesting about the rate of planets. So here are two putative surveys you could set up to do this. So if T is 8, if you look at 8 stars in binary systems, and the occurrence rate of small planets in the habitable zone, small planets includes things, including super Earths in this case. If you look at the occurrence rate of small planets in the habitable zones of those stars, and you assume a single star rate of 0.46, if you find 0 planets, okay, you look at 8 stars, they have a nearly 50% occurrence rate of planets, and you find 0. It's kind of surprising, but it's actually not really statistically significant yet. You have a 2.5% chance of that happening. Even if it's true, even if the occurrence rate is 46% around these stars, you have a 2.5% chance of finding nothing. You know what NASA doesn't want you to do? Spend hundreds of millions of dollars, find nothing, and learn nothing, okay? Finding nothing and learning something, okay. Finding nothing and learning nothing, no bueno. Don't do that. So if you design a survey, you want a null result to be meaningful. You want it to be important. So now let's look at 14 stars. So we have the same single star occurrence rate of 0.46. Let's say we look at 0, we find 0 planets. So we've looked at 14 stars and found no planets. That would suck, but also it would be very unlikely, right? We've got a 0.1% chance that that is going to happen for an occurrence rate of 0.46%. So you need to look at least 14 stars so that a null result, no planets, is interesting. And then you can rule out, if you look at 14 stars in binary systems and you find no planets, you can rule out the single star occurrence rate. Okay, so this is just a little exercise in how do I make sure this is interesting. 2 minutes? Okay, great, because I'm on the last bit. Okay, I know that was a lot of information and maybe not your favorite flavor of information. There weren't a lot of pretty pictures, but it's all concepts I hope seep a little bit in as ideas to be thoughtful about when you're thinking about if you want to do an experiment or if you want to decide if someone else's experiment is useful for you. So here are a bunch of the resources that I used to put this talk together. This was the SIG2 report that I mentioned with experts across all the different detection techniques talking about the metadata you need. This was those FAIR principles, findable, accessible, interoperable, reusable, learn them, use them. This I wanted to point at, Kepler was a mission for statistics, so it did all of those things. And so the Kepler mission page on the NASA Explainer archive has a really nice layout of all of these products. So you and the community, you know you can use Kepler to do all of this because you have everything you need. Your goal, if you ever make a survey, is for it to be as usable as Kepler. And then finally, I did want to point at a couple more papers that talk about setting up a survey mindfully, how to really think ahead about the hypothesis you're testing and how to design your experiment to get there. So there's just a couple of papers here that I wanted to point people at. So thank you very much. In conclusion, no manual vetting and use metadata. Thank you. Oop. Okay.
Thank you very much, Jessie. So questions? Yeah, go ahead.
For this very nice talk, and I think exactly like you. So now I have maybe a task for you. How can the NExScI help us to do properly demographics? For instance, could you have a website? Additional pages dedicated to that? Could you host some of the catalogs where there are uniform stellar properties, or at least links? So, right, it's a question for you.
Yes. So actually that's been on our future plans / wish list for some time. Basically once a year we go to NASA headquarters and say, here's what we could do if we had a bit more money. And the thing I keep saying is we could make an exoplanet demographics interface where we have a website where people could, send us data and we could host catalogs and we could provide frameworks and tools. So yes, that's exactly what I would love to do with the Exoplanet Archive. It's a little beyond our current ability just in terms of resources, but it's something I have locked and loaded for whenever there's time and bandwidth and the ability to do it. Yes, we absolutely can do that. And, we already host contributed data sets. So if you have survey data with any or all of the above attached, you can always send it to us and we'll host it anyway. But the idea would be to bring it all together in an integrated demographics environment. Yes, that's my dream.
Thank you. Any more questions? Yeah, go ahead.
Hello, great talk. I actually had a question about Shira.
Yes.
Big fan of the show. Just kidding.
There's no hyphen in the mission name, so it's not copyrighted.
So how would you predict qualitatively, in terms of its motivation, how kind of wide separation binaries would influence the formation or habitability, long-term habitability of the Earth-like exoplanets that you're looking for?
Yes. So that's, partly when we think about widely separated binaries, most of our sample is within 100 AU between the two stars. We believe that, given inverse square law, if you have another star at 100 AU, you're not really affecting the flux this planet receives on more than a few percent level, much like 100 times 100. You're not getting too much flux. So that's okay. There are systems like Alpha Cen, right, which is actually only 24 AU apart, Alpha Cen A and B. And then you start to think more about, like, if we had another sun where, Uranus is, what would that mean? It starts to become a little bit more important, but it doesn't really shift the habitable zone by huge amounts. Like the habitable zone wiggles a little bit. It's more about the things like long-term stability. And that's actually something we'd like to answer with Shira, right? Like, how frequent are planets in the habitable zones of binary stars? And what does that tell us about the evolution of planets in these systems? So ideally you do a big enough survey that you can start to do interesting things like that. But even ruling out the single star occurrence rate would be fun. Thank you. I'd rather find planets though than find 0 planets. I'll be real.
Great. Thank you very much, Jessie. Let's thank
Thank
our
you.
speaker again.